So we were discussing the torque, speed, characteristics of cumulatively compounded DC motor So we'll be doing the torque speed characteristics of a differentially compounded DC motor and the torque speed characteristics of a cumulatively compounded DC motor. So in case of a cumulatively compounded DC motor, we have seen that the two flux components, the two magnetomotive forces basically add up with each other. Now what we have seen with the cumulatively compounded DC motor, what we have seen is that because of the two flux components, one, you have the flux component produced by the shunt winding, and you have the one flux component produced by the series winding. So if we take the case of a long shunt connection, you see there the series flux is proportional to the armature current, whereas is independent of IA. Fine. You have two field windings. One field winding is in parallel to the armature and another field winding is in series with the armature. So the series field winding, through the series field winding, armature current is also flowing, while as in case of the parallel field winding, the armature current is not flowing, is not a part of the parallel shunt field winding. Now this characteristics is found in a shunt DC motor. Whereas this characteristics is found in a series DC motor. In case of shunt DC motor, the flux produced is totally independent of the armature current and therefore constant with respect to the armature current. Whereas in case of a series DC motor, the flux produced is entirely proportional to the armature current and is entirely dependent upon the armature current. As the armature current varies, the field varies. Now in case of a compounded DC motor, both these two things are combined. So what does a cumulatively compounded DC motor do? It combines the advantage associated with these because of this series effect that is seen in a compounded DC motor. The compounded DC motor has a higher starting torque than a shunt DC motor, but because of the independent nature of field that is also associated in the compounded DC motor, the flux is not entirely proportional to armature current. So what we have seen in case of shunt field winding, we do not achieve higher starting torque, but in case of series DC motor, we are achieving higher starting torques because the flux is entirely proportional to the armature current, and therefore we can achieve actually higher starting torques in case of series DC motor. Now that will be seen in case of a compounded DC motor as well, because it has a series field winding as well. and therefore it will produce a higher starting torque as compared to a shunt DC motor. But it also has a parallel field winding. Now what we have seen in case of a series field winding is that this flux is entirely proportional to the armature current. That will actually cause but because of the nature of because of which we cannot actually load the system directly, as we have discussed in case of a series DC motor. We cannot go for an unloaded connection in case of a series DC motor, but because of the shunt connection also available in case of a compounded DC motor, we can without load also we can start a compounded DC motor. So it actually combines the advantage that are associated with the series winding, that's of higher starting torque, and of shunt winding, that is one is no load starting, as well as it will actually reduce the losses that are actually associated with a series field winding, where the entire winding is in series with the armature winding. So you have some portion of the field winding that is in series, some portion of the series field winding that is in parallel with the armature. So the torque speed characteristics of a compounded DC motor will somewhere lie between the series and the shunt DC motor. It will combine the best features of both these two motors, like it has higher extra starting torque and it will does not overspeed at no load. Higher starting torque cause of series winding, fine, and no overspeeding at no loads cause of shunt field winding. In case of shunt, starting torque is not high. In case of series DC motor, there is an overspeeding at no loads. Now these were two disadvantages with the series and shunt DC motor, but they had their own advantages. Series DC motor has a higher starting torque, and shunt DC motor can be run at no loads directly. So now we are combining both these two features and incorporating that in the compounded DC motor. So therefore, the torque speed characteristics of a compounded DC motor will look somewhere like this. We have seen a series field winding. It's somewhere for series field winding that it's a drooping characteristics. Torque speed characteristics something like this. Whereas in case of a shunt DC motor, we saw the torque speed characteristics somewhere like this. It's almost constant. Now, therefore, for a cumulatively compounded DC motor, the torque speed characteristics will lie somewhere in between. Without actually deriving the speed equation, we can directly see, because of the effect of shunt and series field windings, the torque speed characteristics of a DC series, of a compounded DC motor, of a cumulatively compounded DC motor will be something like this, where this dot represents series torque speed characteristics, this set of dots represents the shunt torque speed characteristics. So in between, what we are getting is compounded torque speed characteristics of a compounded DC motor, of a cumulatively compounded DC motor rather. So we are getting higher speed torque, higher torque as compared to a shunt DC motor, as well as we can go for a no load starting of the DC compound motor. This was about the cumulatively compounded DC motor. Now as far as the differentially compounded DC motor goes, torque speed characteristic will be something like this. Now what is happening here? In case of a differentially compounded DC motor, as we know that the shunt and the series magnetomotive forces, they actually subtract each other. So say for example we are applying a load on this system. As we apply the load, the armature current will increase. As the armature current will increase, the flux that is in the series windings will increase, and the net magnetomotive force, that is FFP minus FFS, what will happen to this? As we increase the load, IA will increase, the armature current will increase. Armature current increases, the series flux increases. That means basically this force will increase. Since this force is constant, so this resultant force, this resultant means the resultant is that the net magnetomotive force decreases. Fine. So it will keep on decreasing. The flux will keep on decreasing as we load the differentially compounded DC motor. The further the decrease in the flux, we know that with decrease in flux the motor tends to speed, since we have established already that the speed is inversely proportional to the flux. So as the flux decreases, the speed of the motor increases. So it will keep on increasing because as the torque induced will increase, this FFS will keep on increasing. It will actually try to make this net magnetomotive force zero or even negative at times. So what will happen is this machine will overspeed drastically, and this type of characteristics will be available to us in case of a differentially compounded DC motor. And the things can even be it can even be that FFS may be greater than FFP. That will actually result in a negative flux being produced in this system. That will actually cause the motor to burn or rotate, it will actually cause the motor to rotate in a different direction, and all of this will actually cause the motor to overspeed. The motor will actually be rotating in a different direction, and it will also cause the motor windings to burn down because of the excessive heat produced in the because of the nature of flux in the system. So because of these characteristics of a differentially compounded DC motor, this type of motor is not used anywhere. We do not actually use it, and it's not actually used intentionally. It can so happen that a cumulatively compounded DC motor may sometimes act as a differentially compounded DC motor because of the reversal of power. At sometimes there may be that the DC cumulatively compounded DC motor, because of the reversal of power, the armature may be rotating at a much higher speed, and the power direction will change, and it will become a DC generator instead of a motor. At that time, this phenomenon may occur that the motor will become a differentially compounded. Instead of remaining a cumulatively compounded DC motor, it will become a differentially compounded DC generator. So to make so this is a thing that is not intentionally used. We are not intentionally building a differentially compounded DC motor. It occurs of its own because of the reversal of power in case of a cumulatively compounded DC motor. Why we do not use a differentially compounded DC motor? Because of the nature of this motor, the net magnetomotive force always tries to decrease, and the flux always tries to approach towards zero. That zero flux will cause a very high overspeeding in this motor. That will actually cause the motor to burn. So practically this motor is not actually used. There is no application of this motor. It can only be a resultant of reversal of power in a cumulatively compounded DC motor or a cumulatively compounded DC generator. Fine. So this is about the torque speed characteristics of a differentially compounded and cumulatively compounded DC motor. Now, if we actually combine the two torque speed characteristics, you can actually show for a cumulatively compounded DC motor, the torque speed characteristic is somewhere like this, and for a differentially compounded the DC motor, the torque speed characteristics is something like this. So this is cumulative compounded, this is differentially compounded, and if we have to show the series and shunt on this, shunt will be somewhere here and the series will be somewhere here. Fine. So this is shunt, this is series. So these are your torque speed characteristics on the same graph for different types of DC series motors, DC motors. For a cumulatively compounded DC motor, it basically takes up the advantage of both shunt and series DC motors and removes their limitations. So it has a torque speed characteristics that lies somewhere in between the shunt and series DC motor. As far as a differentially compounded DC motor goes, the resultant is that the flux always tries to approach zero as the motor is loaded more and more, and the flux tries to approach towards zero. That approach of the flux causes the motor to speed heavily. That will actually cause damage to the motor, and therefore practically a differentially compounded motor is never used. It's only a resultant of the reversal of power in a cumulatively compounded DC motor or a DC generator. So we'll be doing numericals in the next session, and then we'll be taking up the generators.